So there'll be a few chapters that I won't go over, and that's because they're primarily theory. So I think you guys can read through those chapters. And then if you have any questions, you can ask me. I also put up a review assignment for test number 3, which would give you a good indication of what is the critical information to have an understanding of for the theory-related material. So take a look at that after you've read the PowerPoint slides, and if you have any questions, please don't hesitate to contact me. Oh, I should start to record. Does anyone have any questions before we get going?
Hey, Elena.
Hello, Kelly. How are you?
Not bad. For the quiz, is it still Friday?
No, I made the quiz next Thursday, just so I could have it marked by the end of class on next Friday.
Oh, so the wall perimeter isn't for this Friday, it's for next Thursday?
Correct. Yes.
Oh, okay.
Yeah, so it's for April the 8th.
And then test 3 would be the week after?
Correct. It will be April the 16th. And
Okay.
I'm open to a time in which you guys would like to have that test, because I appreciate that your ARP projects are due on the 14th. So if you guys would prefer to write your test in the afternoon on the 16th, I'm open to that. So you guys as a class, just let me know what time you would prefer to write that test, and I'm flexible.
Okay, and for the test 3, is that just the 3 modules?
Correct. I made test 3 this week, and there is more theory than what you would probably be used to, just the nature of the material. So it's about half and half, so half calculations and half theory related.
Okay, and then this quiz, is it just theory, or is there calculations as well?
For the flexible wall permeameter?
Yeah.
It would be calculations as well. So I might give you a graph, and I might say to you, from this graph, tell me what the seepage is between these time intervals. So Fabian, yeah, it would be 12, 13, 14, and 15. So yes, sorry, there are 4 modules. So I might give you a graph, and it would show seepage for, say, the top burette, and I would ask you how much seepage occurred over a specific time period. So it would be interpreting graphs, doing very sort of basic calculations for the quiz, and then the test would be more comprehensive calculations.
Okay, thank you.
Yeah, no problem. There might be one theory question or so on the quiz related to the conducting the actual test. It's hard to believe there's only 4 weeks left, isn't it? Probably
So excuse me. So when we submit our ARP reports, that's basically the end of that class, right?
That's correct. So once they are submitted on the 14th, you're officially done with ARP.
Light bulb moments.
So you have 2 weeks of no class on Wednesday. So that'll be a good day.
I'd rather move geotechnical materials to the Wednesday at that point and then just have the Fridays off.
I'm open to that. I've thought about that as well, because Friday is a downright terrible day to have this course. If you guys as a class are amenable to that, I'm happy to move this class till Wednesday.
But does that mean the exam would move to Wednesday?
I could leave the exam on the Friday if you guys prefer.
Okay.
I'm open again. The last test or last exam is worth, I think, 9%. So it's the test that's worth the least amount. You will have an assignment that will be due the week before, but that's the weight of that assignment is the same as the weight of your final test, or approximately in there. I'll leave that up to you guys. I am amenable to whatever serves you guys best. Okay. Oh, what time is the rough draft due today? For ARP, I would say 11:59 p.m. So you'll have well into the evening. Okay, Taylor's charts. I'm assuming you all can see my screen. Perfect. Okay. There is discussion about infinite slopes prior to Taylor's charts. The expectation is that you'll review the material for infinite slopes, and there's a couple example calculations, and you'll work your way through the example calculations. They're primarily just plug and chug, but if you have any questions regarding the material, don't hesitate to contact me. I did say in an email, I will never test on derivations, and I hold true to that. I've never had to derive anything in my 20+ year career. That being said, I know that some people really like to have a good understanding of the derivations and where the formulas come from and their origins. So that information is presented for those who it interests them. For the rest of you, you don't, or you will never be tested on the derivation of a formula, just on the application of the formula. How would you use the formula and to go through the process. Taylor's charts method is a way in which we can calculate either our factor of safety, or we can use them to calculate what would be the maximum slope, or the maximum stable slope, or the maximum slope angle. It was derived in 1937 by a fellow named Taylor. So you use a stability number or a stability chart method to determine any of those parameters, and they're used for designing stable slopes. So we use these charts to determine, as I mentioned, what the maximum slope angle could be, what the maximum height of the slope could be, or what the maximum factor of safety would be, or what would your factor of safety be to achieve a stable slope. We use the charts, and they're shown on the next two slides, and they're a summary of a number of slip circle analyses that Taylor performed. A number of more recent researchers have published modified or completely revised slope stability charts, but Taylor's charts are the ones that are most frequently cited. The charts use a total stress analysis, so they're not an effective stress analysis, they're a total stress analysis. So the strength values used should be cohesion and friction angle, not effective cohesion or effective friction angle. And you can also have an undrained shear strength with a friction angle of 0 from lab tests on saturated soil. This method applies only to homogeneous slopes with simple geometries. Complex geometries, we would likely use our modeling software, which is a GeoStudio software, and we would use Slope W and likely couple it with Steep W. And again, we can use the Taylor's charts to determine factor of safety, friction angle, slope of the maximum slope, or also we can determine what the maximum height of the slope could be for the slope to be considered stable. There's two charts that were derived by Taylor. The first chart was derived using undrained shear strength. So we've talked about how you would calculate undrained shear strength in the previous modules, especially when you're doing an unconfined compressive strength test, or potentially also when you're doing a UU triaxial test. So we would have an undrained shear strength CU with undrained friction angle of 0. So the chart is shown on the right-hand side of the screen, and you can use this chart for different types of slope failures. So if you have an undrained slope with an undrained shear strength, there's 3 different types of failures. You could have a slope failure. So what a slope failure means is that your failure surface daylights somewhere along the slope face. So if we take a look here, it means that your failure surface is going to daylight somewhere along your slope face. So if you see here, this line in blue, your slip surface will daylight somewhere along that line in blue. So that is a slope circle. That is one type of failure. You can also have a toe circle. So what a toe circle means is that your slip surface daylights at the toe of your slope. So you'll see here that my blue line extends a little bit longer from the top of the slope to the base of the slope along that slope face. And it just means that my slip surface daylights at the toe of the slope. And the third type of slip surface is a deep or midpoint circle. And what this represents is my slip surface will daylight beyond the actual slope face. So you'll see here that my slip surface daylights at a distance from the slope face. So these are the three different primary failure modes when you're using undrained shear strength. And then when Taylor did his multiple slip surfaces analyses, he made this fancy dancy chart over here on the right, and he calculated, it's just an arbitrary value of ND, and I'll show you how you calculate that. You'll see for this slope circle right here, this is the line that you use to determine what your NS value is. You always have an ND value of 1 when you have a slope circle. Your toe circle, typically this is the region in which your ND value would lie for a toe circle, and it's that stippled region that you'll see on the screen. So it's sort of stippled in gray and black. So that's where your ND value would lie for a toe circle failure mode. And then a deeper midpoint circle can range anywhere between an ND value of about 1.2 to an ND value of about 5.52. So this is the chart that we use to determine either our slope angle or our maximum slope height. So say, for example, if I did a calculation and I calculated my ND value to be 1.2, and I knew that my slope height, or sorry, my slope angle was 30 degrees, I could use this chart here. I would draw a line up from here to here. So I would draw a vertical line along the 30 degrees up to my ND value of here, I'll just take it here. It's about 1.1, and then I would draw a horizontal line over to my y-axis, and I would be able to determine my NS value to be 7. And we'll work through the process of what these NS values mean and what these ND values mean. ND, the way you calculate your ND value, I'll show you in the next example problem. So let's work through an example problem. I think it helps cement the material and enables it to make more sense. So I'm going to stop sharing this screen. Switch over. Okay, I'm assuming you guys can see the example problem. We're going to work through example problem 7.4. Okay, example problem 7.4. It's shown here. You can see from this example problem here that it's a midpoint, midpoint or circular failure. You can see that the failure surface daylights beyond the toe of the slope. So it's a midpoint circular failure. In this example problem here, we are provided with an undrained shear strength value of 20 kPa. We have, obviously, if we have an undrained shear strength value, our internal friction angle is 0 degrees. The bulk unit weight of our material is provided, and it's 18 kilonewtons per meter cubed, and the height of the slope is 6 meters. So it's asking you to use the Taylor's chart to determine what is the maximum angle beta that will produce a factor of safety of 1.25. So when you're using Taylor's charts, there's a few formulas that you'll use consistently. The first one is your CUD value. So CUD is equal to CU divided by factor of safety. So with an undrained shear strength example, we're given our CU value, which is 20 kPa, and we know our factor of safety is 1.25. So to calculate our CUD value, it's just simply 20 divided by 1.25. So our CUD value is 16 kPa. The next piece of information we need to know is our NS value. We use our NS value on the Taylor's chart. So NS is equal to your bulk unit weight times the height of the slope divided by CUD. And we just calculated CUD to be 16 kPa. We know gamma bulk is 18 kilonewtons per meter cubed, and we know the height of the slope is 6 meters. So we can go through and plug and chug in the formula, and we can determine our NS value is 6.75. So I'll go to my Taylor's chart. So you'll see from my Taylor's chart, I know what, I don't know what my beta value is, but I've calculated what my NS value is. So the one piece of information that I need to calculate so that I can determine my beta value is my ND value. So you'll see here, I have to know where does my ND value lie on this chart. So I'm going to go back to my example problem. And so ND times H is equal to the total height of the slip surface. So this distance here from the top of the slope to this contact between, say, our clay material and sort of its impermeable boundary or a much stronger or stiffer boundary is equal to ND times H. So I know this total distance here is equal to our ND value times H. I know from this example problem that this distance here from the top of the slope to the base of the slope is 6 meters, and that is our height H. And I know the total distance from the top of the slope to the contact between my weaker clay material and my stronger material is 18 meters. So I know my total value of ND times H is equal to 18 meters, and I know that my H value is equal to 6. So ND times 6 is equal to 18. So I can just use the simple math, and I can calculate my ND value to be 3. I go back to my Taylor's chart. I know that my NS value was 6.75. So my NS value out here. I know my ND value lies somewhere between 2 and 4 because it's about 3. So I'll say this is the approximate point for my ND is equal to 3 line. So they cross about right here. So at about this point right here, my NS line crosses my ND line. So I draw a vertical line down to my x-axis, and I can determine that the maximum slope that I can have for my slope to be considered stable. So my maximum beta value is 10 degrees. So that's how I use my Taylor's chart. This is my undrained shear strength. Taylor's chart. To determine what my maximum slope angle is for the stratigraphy and for the configuration that was presented in this example problem. Does anyone have any? Yes.
Could you, if you were told what your maximum angle was, could you back calculate to get your ND or your NS?
You can back calculate to determine what your height is. So ND, you will always need to have a good idea of. I guess you do need height at that point. Not with undrained shear strength, you can't do it, Sean, but you can do it when you are using cohesion and friction angle. But you wouldn't be able to do it with the undrained because you always have to know your height. I guess you could back calculate what your cohesion would be as long as you know what your height is, but you need height for both NS and for ND. So the only other unknown you could have would be undrained shear strength. So you could back calculate undrained shear strength, but you can't back calculate height.
All right.
So let's go back to here, and I'll give everyone a few minutes to take a look at this example problem. Does anyone have any questions about the process? I'm sure this is all new to everyone. Okay. So this is the example problem that we worked with or we worked through. For the depth of the bottom of your slip surface is always assumed to be at the top of a stronger layer that's beneath the slope. So that's one of the assumptions of using the Taylor's chart. For the case of very deep clay layers, we always use ND is equal to H. So ND and H would be the same value. Don't worry about that so much. Just have an understanding of how you would use your Taylor's charts if you were provided with your slope height, or if you were provided so you could calculate what your maximum slope would be. Or sorry, what your maximum slope angle would be, so your beta value. Okay, there is another Taylor's chart. Oh, what's the little h? It's really the big H, Fabian. So ND is equal to big H. Right, what was phi again? In the case of undrained shear strength, phi is equal to 0. So phi is your friction angle. So with clay material, depending on if it's long-term shear strength or short-term shear strength, your undrained shear strength, so the strength of your material in the short term is your CU value. So, and then phi is equal to 0 in the short term. Whereas if you're looking at long-term shear strength, you would have a cohesion and you would have a friction angle. Okay, so there is a second chart, Taylor's chart, that you can use to determine either your slope angle, or you could also use it to determine what your maximum height would be for your stable slope. So with that, this is the chart you use if your friction angle is greater than 0. So the first chart that we used was if you have an undrained shear strength and your friction angle is equal to 0. This is the chart you use if you have both a cohesion and a friction angle. There's 3 different parameters that you need to calculate when you're using this chart. The first one is NS, the second one is CD, and the third one is phi D. Here I'm going to show. These lines here that are shown on the chart, even though the chart says that they're actually phi, they actually represent phi D. So your phi D calculation, when you calculate your phi D is represented by one of these lines on the Taylor's chart. You can calculate your cohesion because you'll be, or your CD value because you'll be provided with your cohesion in the problem, and you'll be also provided with your factor of safety. And NS you can calculate if you know both your slope height and if you know your CD value. So we're going to work through an example problem using this second Taylor's chart when you have a friction angle greater than 0 and when you're provided with a cohesion value. There is another example problem that you can work through on your own that's very similar to the example problem that we just worked through, where it's asking you to calculate what is your maximum slope angle. So So it's example problem 7.5. It's asking you to calculate what your maximum slope angle beta would be if you have a height of an embankment of 4.2 and a factor of safety of 1.25. So you can work through that on your own. The process is identical to the example problem that I just worked through. We're going to work through example problem 7.6. Example problem 7.6 is asking you, you have a slope that has an angle beta of 40 degrees, and it's asking you to find the height h that will give you a factor of safety of 1.4. So in this example problem, we're provided with our cohesion value, we're provided with our angle of internal friction, which is 12 degrees, and we're provided our bulk unit weight, which is 18.5. So the information that we're not provided in this example problem is h, and that's what we're going to back calculate using the Taylor's chart. So with this example problem here, we're going to start with calculating our CD value. So we know CD is equal to C divided by factor of safety. So to calculate CD, CD is equal to our cohesion value, which is 5 kPa, divided by our factor of safety of 1.4. So our CD value is 3.6 kPa. The next value that we need to calculate is our phi d value. And we know phi d is equal to the inverse tan of the tan of our friction angle divided by our factor of safety. So in this example problem here, we know that our friction angle is 12 degrees. We know our factor of safety is 1.4, and we want to calculate our phi d value. So we can go through and solve for our phi d, which if you go through and solve using these parameters, you can calculate a phi d value of 8.6. So this is our second Taylor's chart. So this is the one we obviously use if we have a friction angle that is greater than 0. So in this example problem here, we know what beta is, and we also know what our phi d value is. So our phi d value is 8.6, and we know beta is 40 degrees. So we're going to draw a vertical line up from beta is equal to 40 degrees. And this is a phi d value of 5, and this is a phi d value of 10. So my phi d value of 8.6 lies approximately along this line here. So I'll draw this line vertically up, and it intersects my phi d value of 8.6 approximately here. I'll draw a horizontal line over to here, so over to my NS. Is that 9.6? No, that should be 8.6. And then I draw a horizontal line over to my NS on my y-axis, and I calculate my NS value to be about 9.6. Does everyone see sort of the process that I use to use the Taylor's chart to determine what my NS value is? Everyone's okay? Okay. So if we have our NS value equal to about 9.6, so we know NS is equal to gamma bulk times H divided by CD. I've calculated CD above. Gamma bulk is given in the problem. I know what my NS value is, so my only unknown in this scenario is my H value. So I can plug and chug through the formula, and I can calculate that the maximum height my slope can be at for a factor of safety of 1.4 to be present with a slope angle of 40 degrees, and the shear strength parameters provided in the problem would be 1.85 meters. So I'll leave that there for a few minutes so you guys can take a look.
Elena,
Mm-hmm.
so in the real world, when would you assume that you have an internal friction angle of 0? Or, yeah, 0.
You sometimes do it when you're doing modeling for excavations. So we'll use Taylor's charts or undrained shear strength when we're going to determine what the short-term stability of an excavation would be. Primarily when we're doing our modeling in the more complex modeling programs, we'll assume a friction angle and a cohesion. So it's more so when you're doing temporary stability of excavations, you'll use an undrained shear strength value.
Okay. So it doesn't really matter what soil it is, you're just going to assume it's 0?
It has to be a clay soil for it to have a friction angle of 0. So it has to be a material that has cohesion. So it would be material that you tested through your unconfined compressive strength testing or triaxial testing.
Okay.
Anyone have any questions on the process? Does anyone want me to go back through any parts of the process? I'm happy to do that. No? Okay. When you're working through your example problems, if you have any questions, don't hesitate to contact me. Has anyone started to work on any of the example problems?
Yeah, some of them.
Some of them. Okay. Have they been making sense, Kelly?
Yeah, it's pretty easy to follow along.
Okay. Yeah, this unit I think is, for this test, is a little bit easier to follow along. And some of it's a review from your hydrodynamics, so I think that's good. Okay, I'm going to work through example problem 7.7. This is the most complicated problem you would see using Taylor's charts. So with this example problem here, what they're asking you to do is to find the factor of safety for a slope using a trial and error approach. So the objective of doing this type of example problem or this type of problem is to find your factor of safety in terms of both cohesion and your friction angle separately, and repeat this until the two values of the factor of safety for your friction angle and your cohesion are equal. So in this instance here, you don't know what your factor of safety is, but you know what your slope height is, you know what your bulk unit weight is, you know what your cohesion is, your friction angle and your slope angle. And you want to determine what your factor of safety of your slope is. So it's just a trial and error approach. So with this approach, what the very first step we do is we're going to assume a phi d value. And the way we determine what our initial phi d value assumption will be is whatever friction angle is given to us in the problem, we're going to assume that our phi d value is equal to that friction angle. If we assume that our friction angle, our phi d value is equal to our friction angle in the problem, then we know that our factor of safety is equal to 1. So in this example problem here, our friction angle was 18 degrees. So I'm going to assume that my phi d value is also 18 degrees. And therefore, my factor of safety for my friction angle is equal to 1. So I can use my Taylor's chart at that point. If I know my phi d value is 18 and my maximum slope is 60 degrees, I can calculate my NS value. So what I'm going to do is I'm going to use the bottom Taylor's chart. So if I know that I have a slope angle of 60 degrees, I know my phi d value is 18. It's about here. Going to draw a line vertically up till I intersect about this point right here. And I'm going to draw a vertical line over. And where this horizontal line intersects my y-axis, my NS value is somewhere between 9.7 and 9.8. And I'm just using the information from the problem. So here I just assumed my NS value was 9.7. I know NS is equal to gamma bulk times my slope height divided by my CD value. So if I know NS is equal to 9.7, I know my gamma bulk value is equal to 18.5. I know my slope height is 3.5. The only unknown that I have is my CD value. So I can plug and chug through this formula here to calculate my CD value, and I can calculate my CD value to be 6.68. So I know CD is equal to my cohesion value divided by my factor of safety. If I know my CD value is 6.68 and I know that my cohesion value is 12, the only unknown I have is factor of safety. So if I go through and solve for this problem, I can determine that my factor of safety for my cohesion is 1.8, and I know that the factor of safety for my friction angle is 1. So what I do is I draw a handy dandy little chart or graph here where I plot friction angle on my y-axis, and I plot factor of safety for my friction angle on my y-axis and factor of safety for my cohesion on my x-axis. I have the same scale. It's a 1-to-1 scale, and I draw a 1-to-1 linear line. So this dashed line is simply just a 1-to-1 line drawn at a 45-degree angle. So what the end goal of this is to plot 1 or 2 data points below this 45-degree angle line and a maximum, and 1 to 2 data points above this 45-degree line. So you'll see here, I know that I have a factor of safety for my cohesion to be 1.8. So I put the data point here because I know also my factor of safety for my friction angle is 1. So with a factor of safety of 1 for my friction angle and a factor of safety of 1.8 for my cohesion, that data point plots right there on my graph. So right now, obviously, I only have 1 data point that lies beneath my 45-degree angle line. So I have to go through and do a minimum of 2 more iterations. So I have at least 1 data point above the line and at least 1 to 2 data points below the line. So now I'm going to go through the process again. And again, I'm just assuming another phi-d value. So in this instance here, I assumed a phi-d value of 15. It doesn't matter what you assume your phi-d value is. You could assume that your phi-d value is 14 degrees, or you could assume that it's 13 degrees. It's just an arbitrary value. You know, you shouldn't assume a phi-d value that's greater than your friction angle that's provided in the problem. You know you're always going lower than the friction angle that was provided in your problem. So we started with 18. We recognize that our factor of safety for our cohesion is too high. So we know that we need to reduce our phi-d value. And we know so we know we have to reduce our friction angle. So here I've reduced it by 3 to 15. Again, you could have picked 14 or 13, that would be okay. So to calculate our factor of safety for our friction angle, I'm simply using the tan of 18 degrees. So I'm taking the tan of my friction angle and dividing that by my tan phi-d, and that's going to provide me with my factor of safety value. So I know my factor of safety when I have a phi-d value of 15 degrees is equal to 1.2. So again, I'm going to go through the same process that I went through previously, where I'm going to use my Taylor charts to determine what my NS value is. So my slope angle remains constant at 60 degrees. And now I'm going to go up and I'm going to go to where this 60-degree slope angle intersects my phi-d value of 15. So my phi-d value of 15 lies along this line. this dark line that's shown here. I didn't have to interpolate between the two lines. I can draw a horizontal line over to my y-axis so I can determine what my NS value is. So in this instance here, I would assume my NS value is about 8.8. So I'll go back. If I know my NS value is 8.8 and I know my bulk unit weight is 18.5 and the height of my slope is 3.5, I can go through and calculate my CD value. So I've calculated my CD value to be 7.4. And then I can go through and calculate what my factor of safety associated with my cohesion is. And I've calculated it to be 1.6. So I have my factor of safety for my friction angle is 1.2, and my factor of safety for my cohesion is 1.63. So that plots about right here on my graph. So that would be my second data point. So you'll see with this graph, you need to have a minimum of one data point that lies above the line. Otherwise, you can't do a proper interpolation. So I have two data points that lie below the line, so I need a minimum of one data point that lies above the line. So my next assumption, and again, I'm just assuming a value, I assumed a 5E value of 12. And I went through the same process to calculate factor of safety and for both my friction angle and for my cohesion. So going through the same process that we just worked through, I calculated my factor of safety for my friction angle to be 1.5 and my factor of safety for my cohesion to be 1.45. So that data point lies right there. So it lies just above my 1-to-1 line. So what I would do is I would connect those three data points with a line. It doesn't have to be a linear line. It could have a bit of a curve to it or a bit of a bend to it. But I would connect those three data points. Where this line here that I plotted as I've gone through the process to determine my factor of safety for cohesion and also for friction angle, where that line intercepts my 1-to-1 line that I drew on my graph, that is my factor of safety for my slope. So you'll see here that this line here, so my line of best fit for my three data points intercepts my 1-to-1 line right here. So I draw a vertical line down to my x-axis, and I can determine at a factor of safety value of 1.45, my factor of safety for my friction angle and my factor of safety for my cohesion are the same. So therefore, I know that my friction angle my factor of safety for this slope is 1.45. You could pick a second one that was low. So Fabian asked if you could pick a second one that was low. So yeah, if you're at 18, you could pick a second one that was around 8. I do recommend that you have 3 data points on your graph. It gives you better accuracy in determining your factor of safety. But you could pick a second one that was low. So if you want to go down to 8 or something like that, you could. But just have a minimum of 3 data points. So that's how you would go through and determine what your factor of safety is for a slope using Taylor's charts if the only unknown you have is factor of safety. So if you know what your height of your slope is, you know what your bulk unit weight is, your cohesion, your friction angle, and the slope angle, you can use Taylor's chart to determine your factor of safety. Anyone have any questions on the process?
We could expect something like this on the test?
I could potentially put something like this on a test. I want you to understand the process. I don't know if I will. And the reason why I'm saying that is because in the real world, you're going to use slope stability modeling software. You're not going to go through and do 3 or 4 iterations to determine what your factor of safety is. You're going to put it into modeling software and the program will spit out your factor of safety for you. You will have a Taylor's charts question on the test. I just don't know if I'll actually give you this one. Does that sound fair? So guaranteed there will be a Taylor's charts question on your test. I just don't know if I'll give you this one.
Okay, sounds good.
Okay. So I think in your presentations where you're reviewing the theory material, it talks about slope W or using GeoStudio to calculate your factor of safety. That's what you do in industry. That's the program that you use to determine what your factor of safety is once you know your shear strength parameters. When I was in school 20 years ago, we used Taylor's charts and method of slices because those computer models didn't exist. So we used to have to calculate our factor of safety for every scenario. If you're using method of slices, you used to have to calculate your factor of safety for every slip surface, whereas this computer program now can model thousands of slip surfaces in like a second or two. So it used to take us 5 to 10 minutes to analyze one slip surface, and now we can analyze thousands in a couple seconds. So technology has progressed significantly in the last 20 years. Again, this is good information to know, especially when you're looking at temporary excavations in the Winnipeg area. Like if you're out in the field and you have a contractor who wants to dig a temporary excavation, maybe you're putting in a water line or something like that. Obviously, there's workplace health and safety requirements for how deep your excavation can be before storing is required. But if you want to do a quick and dirty calculation, you could use something like Taylor's charts. Okay, why don't we take a 10-minute break? So why don't we reconvene at 10:05, and at that point, if we can start with flexible wall permeameter testing. Anyone else have any questions on Taylor's charts or the use of Taylor's charts? Do make sure you do review the material prior to Taylor's charts. So the material on infinite slope and calculating factors of safety for infinite slopes. So do make sure you review that material as well. Otherwise, we'll reconvene at 10:05 and we'll go through flexible wall permeameter testing, if that works. Okay, so we'll come back at 10:05. How's everyone's ARP reports coming along?
I guess not very good if all I hear is crickets chirping.
No, I'm a little worried. Or everyone's busy working on them right now.
Yeah, that must be it.
Yeah, we'll go with that. Okay, one more minute and we'll start with flexible wall permeameter testing. Okay, it's 10:05, so I'll start. now with flexible wall permeameter testing. So we use flexible wall permeameter testing to measure the hydraulic conductivity of fine-grained soils. So you're probably wondering, why do we need to have a good understanding of the hydraulic conductivity of fine-grained soils? There's, multiple reasons. I'll give you a couple examples. Say if we were to construct a flood protection dike, we would have to have an understanding of what the hydraulic conductivity of the embankment structure itself is. So we need to have an understanding of its conductivity to determine if it's actually going to hold back water, because there's no point in constructing an embankment that's not able to hold back water. So if people are dependent on this embankment for keeping their houses dry and their community safe, we need to ensure that we have a sufficiently low hydraulic conductivity. The same with, the foundation material beneath a flood protection dike. If the foundation material beneath a flood protection dike is quite porous and it has a high hydraulic conductivity, again, the flood protection dike isn't going to keep the community safe. People's houses will flood and there would be significant damage. So this is an example of where we would have to have a good understanding of the hydraulic conductivity of both the embankment structure and the foundation. Another example would be clay liners for landfills or sanitary lagoons. You have to measure the rate at which water is going to be able to penetrate or flow through those clay liners. And obviously there's requirements from the Department of Conservation that you need to adhere to. So you have to have a good understanding of the hydraulic conductivity of that clay liner, because otherwise you could have the groundwater leaching through and it would be pretty stinky, and we don't want to contaminate groundwater in the area of a sanitary lagoon or a landfill. So those clay liners prevent the contamination of your groundwater table. So to predict those seepage volumes, we have to have a knowledge of a soil's hydraulic conductivity. Flexible wall permeameter is one type of testing that facilitates determining your hydraulic conductivity of a fine-grained soil. You can either use a Shelby tube sample, so a relatively undisturbed sample, or a remolded specimen to determine your K value. Our flexible wall permeameter test, it applies to one-dimensional flow or one-dimensional laminar flow within porous materials such as soil and rock. This test method only applies to material or a soil that is saturated. So your specimen can't contain air, because that will give you a false indication of your hydraulic conductivity. And it also inhibits the ability to properly measure the hydraulic conductivity. For the flow to be considered laminar, Darcy's law has to be assumed to be valid. So that is one condition of the flexible wall permeameter test. We assume Darcy's law is valid and flow is laminar. The K value that you calculate in the lab is sometimes different than the K value that you will experience in the field. The great thing with flexible wall permeameter tests is you can perform them under conditions that are very similar to the conditions that are experienced in the field. So you can apply a confining pressure and you can apply a back pressure that are very similar to the overburden stress and the pore water pressure that would be experienced by that mass of soil in the field. The correlation between hydraulic conductivities attained in the lab with those in the field or those of in-place field materials have not been fully investigated. So the two values are sometimes different, and you do have to apply the lab results with caution. And I think a good way to look at this is when you're taking a specimen from the field, so you take a Shelby tube sample, that specimen or that sample is from a very discrete point within the soil mass. But if we think of the soil mass as a much larger mass, so we think of that clay material as a much larger mass of soil, there are inherent differences. You may have some laminations within your clay that have higher hydraulic conductivity than the clay specimen that you took either through the Shelby tube sample, or if you made a remolded specimen, then the remolded specimen that you prepared. So that's likely one of the reasons why there may be differences in the K value you measure in the lab versus the K value that's actually experienced in the field. Darcy's Law. I'm not going to spend a bunch of time on this. I think you guys took this in Mike Robb's class last year. So just remember, Darcy's Law, Q is equal to Kia. So Q represents your flow of water in meters cubed per second. K is your hydraulic conductivity of your soil material. And it can either be reported in meters per second or in centimeters per second. And your K value is only dependent on the soil type. I is your hydraulic gradient. So your hydraulic gradient is equal to your head differential divided by the length over which you have that head differential. And A is the cross-sectional area that you're calculating your flow rate for. Darcy's Law applies only for laminar flow, so it doesn't apply for turbulent flow. It's only laminar flow through a porous material. So a porous material would be either soil material or through bedrock material. Does anyone remember Reynolds number? Did you guys do this in Mike's class?
Yes.
Okay. So Reynolds number comes into play when determining if a flow is laminar or not. This is the formula here for Reynolds number. I'm not going to test you on this. This is just sort of to give you a bit of the background. So your Reynolds number always has to be less than 10 for flow to be considered laminar. So if we think of flow in terms of a clay material, our velocity or our seepage velocity is always quite low because it's a clay material, and the particle diameter is small because it's a clay material. Our water viscosity is somewhat constant, or it is constant. So to achieve a Reynolds number of less than 10 for a clay material is not difficult. If you have a sand material where you have a higher seepage velocity and a larger particle diameter, then it is more difficult to ensure that you have a Reynolds number of less than 10. That's why we primarily test clay material with our flexible wall permeameter test. These are typical values of hydraulic conductivity that you would see for sand and gravel material all the way up to a swelling clay material or a bentonitic rock. Hydraulic conductivity values are measured in an order or in orders of magnitude. So I don't expect you to memorize what these orders of magnitude are, just recognizing that the K value for a sand and gravel material is always much higher than it is for a clay material. So having a K value of 10 to the minus 3 for a clean sand and gravel is reasonable. If you told me your K value for your clay material was 10 to the minus 3, maybe double check your calculations because likely something's not right. Like you should have a K value of at least 10 to the minus 8 in that range for a clay material. And that's in meters per second. If you're asked to provide your K value in centimeters per second, just divide your K value in meters per second. Sorry, you multiply that by 100. Constant head tests. So there's two types of constant head tests that can be performed. The two types are both there are two types. The first one being a rigid wall constant head test, and the second one being the flexible wall permeameter test. So this part of the lecture, I'll concentrate on the flexible wall permeameter test. I'll talk about the rigid wall permeameter test in the next hour. But they're called constant head tests because the head difference, or the delta H across your specimen, stays constant throughout the test. So you're not changing your delta H value throughout the test. That's why it's called a constant head test. Your rigid wall permeameter tests are used for material that is coarser grained, so for a sand or a sand and gravel, and these coarser grained materials have a higher seepage rate. Whereas a flexible wall permeameter test is used for a fine grain material that has a very slow seepage rate. The formula that you use for both your rigid wall and your flexible wall permeameter tests are the same. So this is the formula that you use for both tests, where your hydraulic conductivity K is equal to Q. So Q represents a volume of water. So Q would be reported in millimeters or in liters. L represents the length of your specimen. So you'll see here, this represents the length of your specimen. Same with if you're doing a flexible wall permeameter test, it's just the length of your specimen. So likely you would get a specimen from a Shelby tube and cut it into a smaller dimension. Usually we use around 50 millimeter length for the specimens, sometimes a bit larger. Area represents the area of your specimen, so you'll know the diameter of your specimen, so you can just calculate the area. And delta H represents your head difference. And you can measure that head difference by either knowing what your pressures are or the difference in your pressures, or in the case of a rigid wall permeameter test, you can just measure your head differential on the tubing. Flexible wall permeameter test, you know what your head differential is because you're applying two different pressures to the top and the bottom of the pressure, or sorry, top and bottom of the specimen. So your flexible wall permeameter test, again, I've sort of had a discussion on the formula and what each of the different parameters in the formula stand for. Remember, do you guys remember the flow of water? Does water flow from high head to low head or low head to high head? Remember this from Mike's class? Right.
High head to low head?
Correct. So water always flows from high head to low head. So if you're applying a higher pressure at the base of your specimen and a lower pressure at the top of your specimen, then water is going to flow from the base of the specimen to the top of the specimen. So in the case of a flexible wall permeameter test, the way you calculate your hydraulic gradient, so your hydraulic gradient I is equal to delta H over L. You know the length of your specimen, but you actually don't know the head differential. Like you don't have any tubing that you can use to measure the head differential. But you know the difference in pressure that you're applying to the base of the specimen and to the top of the specimen. So the way you calculate your delta H is P1 is your high pressure that you're applying, P2 is your lower pressure that you're applying, and you're using a medium of water in a flexible wall permeameter test. So you divide your P1 minus P2 in your numerator, and you divide that by the unit weight of water. P1 and P2 are measured in kPa, or sometimes in PSI, and you convert them to a kPa. So you can calculate your delta H in that manner. And then you know that your length of the specimen, so you can determine what your hydraulic gradient is. You use pressurized water in a flexible wall permeameter test to provide confinement to the specimen. In a flexible wall permeameter test, you place your specimen in a flexible wall permeameter cell. Your specimen, you put a latex membrane around the specimen, and you put porous stones above and below the specimen with some filter paper as well. And you'll have a top and a base cap on your specimen. With a flexible wall permeameter test, there's a few assumptions that that are used with this test. The first one is that your material is always saturated. So unless your material is saturated, you're not able to conduct your flexible wall permeameter testing. So if we were to do this in the lab, we would usually, we would prepare the specimen, put it in the flexible wall permeameter cell, and then we would saturate and consolidate the specimen consecutively or simultaneously, and that would take us about a week. And so once the specimen has undergone saturation and consolidation, then we would be able to begin our permeation phase or calculating what our hydraulic conductivity is for that specimen. Flexible wall permeameter test, as I mentioned, can only be conducted on material that has a low hydraulic conductivity. So I would say less than 10 to the minus 6 meters per second. Otherwise, you would use the rigid wall constant head test. The one benefit of your flexible wall permeameter test is you can control the effective confining pressure. So what I mean by that is the flexible wall permeameter test provides a means for controlling your effective stress because you apply an internal water pressure, which is referred to as a back pressure, and an external confining pressure or your cell pressure. So you apply your confining pressure from the top, so it's applied laterally, and your back pressure is applied loaded axially, and your back pressure is applied laterally. And your cell pressure and your back pressure, you can design your test so that these are representative of your field conditions. So your confining pressure can be representative of your overburden pressure in the soil, or if you're going to be adding an external load, it could be representative of your final effective stress, and your back pressure can represent your pore water pressure conditions in the field. So that's sort of the background on flexible wall permeameter tests. I'm going to pause there to see if anyone has any questions on the background. No?
When you guys were like physically in the labs, did you guys actually like each group do a sample each, or was it like 2 tests for the whole class kind of?
No, everybody had their own specimen. So you would be in lab groups of 3 students, and everyone did a test on their own specimen, or each group did a test on their own specimen. So say in your class, you would have had, well, 3 lab, so 12 lab groups per session. And so you would have had 3 students in each of those. Or sorry, I had 12 lab groups in total. So there would be 6 lab groups per session. We have 6 flexible wall permeameter cells. So each lab section could run the test. It would take about 3 weeks, but no. So Cole's asking, is this PowerPoint everything we need for the quiz? No, you will need to go through the lab handout, and I also gave you a set of lab data. So go through the data analysis interpretation and the plotting of the data that I provided, and make sure you have a good understanding of how I did the interpretation of the lab data. I'll go through an example problem, and when I go through that example problem, that will give you a better understanding of what would be on the lab quiz. So yeah, so if we were in the lab, each lab group would be doing their own test. So the test would take 3 weeks. So one lab group, say if you were the Monday AM lab group, you would have 3 weeks to run it. And then after that, the next lab group would run it.
Oh,
it would take a, yeah.
Sorry, is that still on the table, like coming in after graduation? Or is that not?
For those, no, for those who are interested, I'm happy to run a little session where we could go through some of the lab tests.
Okay, perfect. Thank you.
I'll send an email out. They're doing the second years first, just because they wanted them to have an understanding of the index testing, and they thought it would help with their employment opportunities. They didn't have like a huge uptake on it. So I think it's only going to be 1 week. But the second week, like whoever's available, I'm happy for students to come in, and I can show you how to do a UCF test, direct shear. I can show you how to initiate a flexible wall. Like some of the tests take 3 weeks to run. Some of them can be run in an hour or 2. So, but we could go through the various tests that we talked about in class, and I could show you how to do the setup and how you would collect the data.
Okay, awesome. Thank you.
No problem. Okay, there's three components to a flexible wall permeameter system. The first one is the constant head system. So if I look at this here, all of this in here is referred to as the constant head system. So within the constant head system, you have an air pressure supply, you have a top and a base regulator, you have a regulator for your cell pressure, a regulator for your back pressure. You also have a water-filled tank for filling your flexible wall permeameter cell and for applying your back pressure. So that's your constant head system. You also have a flow measurement system. So if we look at our flow measurement system, it's simply this small component here. So your flow measurement system would include two burettes. You would have differential pressure transducers to measure the change in water levels. So that is what is encompassed within your flow measurement system. And then within your permeameter cell, we'll do it in a different color. So this would simply represent your permeameter cell system. So within your permeameter cell system, you would have a permeameter cell, you would have vent lines. So those vent lines allow air bubbles that are trapped within your specimen or trapped within the lines to be removed. So you have your specimen. Your specimen is encased in a latex membrane. There's a porous stone above and below your specimen, and there's some filter paper. You also will have a top and a base cap on your specimen as well. And then there's obviously the flexible wall permeameter cell. Your direction of seepage or your direction of flow is always from the base of the specimen to the top of the specimen. So yeah, the area identified in green is your permeameter cell. Okay, so as I mentioned, there's sort of it's a two-step process for conducting your flexible wall permeameter test. The first step is where you would prepare your specimen. So we always say your specimen needs to be greater than 25 millimeters in length, and same with your diameter. We usually used a 1-to-1 ratio, so we usually had a diameter around 50 mils, and we had a specimen length around 50 mils. You would place your specimen in the flexible wall permeameter cell. You would fill that cell with water. Your specimen would be sealed in a latex membrane with porous stones or filter stones above and below it. The water that we're using for this test is de-aired. All of your lines that are used within the system are also flushed so that we don't have any air within the system. After the setup's complete, we would apply a confining pressure, so a cell pressure, and we apply a back pressure. As we're applying the back pressure and the cell pressure, we're also saturating the specimen. So we're pushing water through the specimen under pressure so that we can saturate the specimen. So if there's any remaining air in the void space, that air is pushed out and that we're saturating the specimen. Our confining pressure consolidates the soil. So when the soil becomes saturated, it's also consolidating it at the same time. So that's the first stage of our flexible wall permeameter test. It takes about a week. And during this phase, we're measuring the volume of water flowing into and out of the specimen. So we're recording this daily through the burette. And then we also have our P3, and we are recording data about every 10 minutes. So it eventually gets to the point where the volume of water into and out of the specimen, you're not really recording anything, and it remains constant. So your lines sort of plateau, or your measurements plateau. So that's when we know that the specimen is consolidated and saturated. One thing to note is your confining pressure that you're always applying to the specimen, it's always greater than your back pressure. So with the test, we generally have a confining pressure of 20 psi, and we have a back pressure of 15 psi during the saturation phase. So that's the first stage. So as I mentioned, that takes about a week. So then you would come in the second week, and you would change the configuration of the setup slightly, and then you would begin the permeation phase of your test. So in the permeation phase, we force water to seep through the soil because we apply a base pressure at about 15.5 psi, and our top pressure, so the top of the specimen, has a pressure of about 14.5 psi. So we have about a 1 psi or 7 kPa pressure difference between the base and the top of the specimen. So the volume of water going in should equal the volume of the water going out if the soil is saturated. So we measure that over about a week time period as well, and we're able to measure the volume of water going in and out. And they should be approximately the same. I've never had lines that completely overlap, but they're in the same general ballpark, unless you have malfunctioning of a sensor or of a burette. So this would be the second part of the test. Again, it takes about a week. So then when you come back in the third week, you just download the data, and then we would spend the lab period doing data interpretation. This table here just gives you a general indication of what your expected K value is for when you're doing hydraulic conductivity testing on clay. It also gives you an idea of what your hydraulic gradient can be so that you can ensure that your flow is laminar. And it also gives you what your maximum pressure differential can be between the top and the base of the specimen to ensure that your flow is laminar. So a lower expected hydraulic conductivity value allows you to use larger hydraulic gradients. This slide here, and we'll talk about this in the next PowerPoint as well, just talks about temperature correction. So when we're measuring or determining what our K value is, we always assume that the room temperature is at 20 degrees Celsius. However, we all know when we go into B109, when there's 18 of us in there, the temperature in the room is usually above 20 degrees Celsius. Then everyone leaves and the temperature usually goes below 20 degrees Celsius. But in general, if our temperature is above 20 degrees Celsius, when we're determining what our K value is, if we know the room temperature is generally greater than 20 degrees Celsius, we apply a correction factor to our calculated K value. So say, for example, I'm going to take this data point here. If I knew my average room temperature was 24 degrees Celsius when I was conducting the test, and I determined my K value to be 1 × 10⁻⁹ meters per second, I would multiply my K value that I calculated by this 0.90945. And that's just because the water temperature affects viscosity. So as a result, it will also affect the flow rate through a soil. So viscosity is resistance to flow. So if you think of maple syrup doesn't flow as easily potentially as water does. So at higher temperatures, water tends to flow faster than what it would flow at 20 degrees Celsius. And we're always referring to K at a 20 degrees Celsius temperature measurement. Whereas if the temperature was at 17 degrees Celsius when we did our test, the hydraulic conductivity that we calculated would be lower than what it would have been if we were able to conduct the test at 20 degrees Celsius. So that's how you would use this table here. So I'm going to pause here before I continue on. Anyone have any questions on the information that I presented? There's a video that Rainan prepared of him conducting the flexible wall permeameter test. So I think he showed you how to prepare the specimen. The specimen was set up. I set it up in the flexible wall permeameter cell, and then I believe he talked about how the test is conducted. No questions? Okay, typical test results. So this is the saturation and consolidation phase. So saturation and consolidation occurs simultaneously. We just don't have time to have it occur 1 week for saturation, another week for consolidation. The total volume of water going into and out of the specimen is measured. So the purpose of this measurement is to ensure the specimen is saturated and there's no leaks in the volume measurement equipment. So if there's no water going into or out of the specimen, so what we mean by that is this plot of this line here is relatively horizontal, then we're ready to start the actual permeability test. If we were down in this region here and there were significant differences on a daily basis in the total inflow of water, then you know that the saturation process is still occurring and that you shouldn't begin the actual permeation phase or the seepage phase of the test. So as I mentioned, it takes about a week for these lines to stabilize and for them to plateau and be roughly horizontal. The seepage phase of the test is the volume of water flowing. So you're measuring the volume of water flowing into the bottom of the specimen and the volume of water flowing out of the specimen. So if your specimen is saturated, the volume of water flowing into your specimen should be equal to the volume of water flowing out of your specimen. So you would measure your Q value and you would plot your Q value or your cumulative flow versus time. During the seepage phase, the plot of your flow at the base of the specimen and your flow at the top of the specimen, they should be approximately equal. That's shown on this graph here. That being said, I've never seen plots where they're actually 100% equal. There's usually some variations in the plots. The way that we use this seepage data is we're concerned with determining what is a Q value over a certain period of time. So it's easiest to do this over a linear or over a straight portion of your curve, or sorry, of your line. So you'll see in this example problem here, I'm taking a time period of, so I have about 4,200-ish here, and I have about 10,200 here. So the change in time over this portion, so this is my linear portion of the line. So the change in time over that linear portion of the line is about 6,000 minutes. And I can just determine that by looking at data point 1 and data point 2 and determining what the time is by looking at the x-axis. My Q value, I determined that value over that time period by looking at, by taking the difference between my Q value at, this data point here and my Q value at this data point here. So my Q value at this data point here is around 13.8 millimeters, and my Q value at this data point here is about 6.3 millimeters. So if we go 13.8 and then take away 6.3, I get about 7.5 millimeters is my Q value, my average of your flow in and out over that time period between about 4,200 minutes and 10,200 minutes. So that's how I would determine what my Q value is. I'll work through an example problem with you guys. So we're able to delve into this in a little more detail. But I'm going to pause here before we go to the example problem to see if anyone has any questions. No questions. Okay. Is everyone okay if I go over this example problem here? Okay,
Go for it.
perfect.
Yeah.
Okay. So this is lab example problem 5.2. Don't worry about lab example problem 5.1 because I find that that one's a little confusing. So I would just stick to this one here and don't worry about example problem 5.1. Here we have, it says the saturation of a specimen is shown in the attached plot. About 5 millimeters of water enter the specimen over 2.5 weeks. It gives you a specific gravity, it gives you a length of the specimen, the diameter, its dry mass, and its initial moisture content. And then it says calculate the hydraulic conductivity in centimeters per second and meters per second if the top and bottom pressure difference is 2 psi or 13.8 kPa. So there's there's a lot of extraneous information that's provided in this problem here. The first of it being specific gravity. It doesn't really matter what your specific gravity is when you're determining your K value. You're not going to use your specific gravity. You're not going to use your dry mass, and you're not going to use your initial moisture content. So you know K is equal to Q times L divided by T, A delta H. So the first thing that you should do when solving this problem is determine over which time period you're going to calculate what your Q value is. So you'll see here, and as I sort of mentioned earlier, you have your volume of water into the base is represented by this top line here, and your volume of water into the top of the specimen is represented by this dark line here. In an ideal world, these lines should overlap one another, but I've never seen them overlap one another. So there'll be slight differences or nuances in the line. So when we're trying to determine our volume of water into and out of the specimen or determine what our Q value is, we take an average of our Q value. So our Q value average is equal to Q top plus Q base divided by 2. So I need to determine what my Q top is and what my Q base is. So if I look at the graph here, you know, it's not overly linear, but I would take the data between about 6,000 and 10,000 minutes. And you can just sort of assume that the line is linear. So you can just take one data point here at 6,000 for the base and one data point here at 10,000 for the base. So you know the T value or your delta T is 4,000 minutes. So you can take a look here and you can say, okay, at my Q top, that was about 4.6, is it? And at the base, it was about 3.0. So my Q into the base of my specimen over that 4,000 minute time frame is equal to 4.6 millimeters minus 3.0 milliliters, which is equal to 1.6 milliliters. So I know over that 4,000 minute time period, I had 1.6 milliliters into the base of my specimen. And so let's look at the top of my specimen. It looks like I had about 4 milliliters in at 10,000 minutes. So one data point here, about 4 milliliters. And it looks like I had about 1.9. Maybe 1.8-ish. And that was that's probably about 3.9. 3.9 minus 1.9. There's a bit of interpretation with this, so we'll say it's about 2 milliliters difference over this 4,000 minute time period for the volume of water into out of the top of the specimen. I guess initially I said it was about 1.9. Here I got about 2. there is leeway. Yes, it is super approximate. There is leeway within your answers, so there is a range that I would accept when determining what your Q value is. It's just doing your best interpretation of the data that's provided. So I would say my Q out, so my Q base is about 1.6, my Q top is about 2. So I would take the average of my top and my base, and so here I would have 1.6 plus 2 divided by 2. So here my average would be about 1.8 milliliters, and 1 milliliter is equal to 1 milliliter is equal to 1 centimeter cubed. So I can just simply convert 1.8 milliliters is equal to 1.8 centimeters cubed. So I know what my average Q is between 6,000 minutes and 4,000 minutes. So if I look at K, so I know my Q average is about 1.8 centimeters cubed. I know the length of my specimen is 10.27 centimeters. So the one thing to be really careful about when you're calculating your K value is to ensure consistency in units. So if you have a Q value in centimeters cubed, make sure your length and your area are also using centimeters. So my length in this problem was provided in millimeters, so I needed to convert it to centimeters. So 102.7 millimeters is equal to 10.27 centimeters. So that's my numerator. On my denominator, I need T, so I know T is 4,000 minutes. I have to convert my minutes to seconds because K is always measured in centimeters per second or in meters per second. So to convert minutes to seconds, I multiply by 60 because there's 60 seconds in a minute. This portion of the equation here, I'm calculating my area of my specimen. So the diameter was provided, and I converted my diameter to a centimeter, and then I'm calculating what the area of my specimen is in centimeters cubed. And then my final conversion is I have to calculate what my delta H is. So to calculate delta H, so remember delta H is equal to P1 minus P2 divided by the unit weight of water. So the problem told me that my P1 minus P2, it was 2 PSI or 13.8 kPa. And then I divide that 13.8 by the unit weight of water, which is 9.81, and we can put that down here, kilonewtons per meter cubed. And then I'm going to convert that value to centimeters because there was 100 centimeters per meter and all the other units in my problem were in centimeters. So I can go through after I've done all those conversions and I can calculate my K value to be 1.4 times 10 to the minus 8 centimeters per second. It's always easier when you're calculating your K value for a flexible wall permeameter test to calculate it in centimeters per second, because your total seepage volume is always going to be given to you in milliliters, and it's much easier to convert 1 milliliter is equal to 1 centimeter cubed than to be going through and converting a milliliter to meters cubed. And then once you calculate your K value in centimeters per second, that's equal to 1.4 times 10 to the minus 10 meters per second. So it's easier to convert from centimeters per second to meters per second than to do it initially in the problem. How did I get T is equal to 4,000? It's because, Cole, I just took my values between T is equal to 6,000 and T is equal to 10,000. So it's just a time differential between the two data points that I used. If you wanted to use a data point at T is equal to 4,000 and T is equal to 10,000, and you would have a different time increment, that's totally fine. It's just you would have a different Q value associated with that time increment. So you're free to pick whatever time increment you want. It's just you'll have a different Q value associated with that time increment, but that's okay. So it's sort of arbitrary where on this graph you take your data points. I wouldn't take it initially like down in the 0 to 2, but usually once you get beyond 3 or 4,000, it's okay to take your data points in that range. So this would be representative of what you would see on the quiz. I would tell you the time increment, and I would ask you to calculate what your volume of water would be, either into the base or out of the top. This is very representative of a question you will see on your test, where I will just give you the data and tell you to calculate what your K value is. I could ask you to calculate your hydraulic gradient. Looking at this data here, and you know that your hydraulic gradient is equal to delta H over L. You can calculate delta H, and you know what the length of your specimen is, so you're able to calculate what your hydraulic gradient is. So those are more types of questions that I would ask you on the quiz, and then solving for your K value is a question that I would ask you on the test by giving you data. It would be fair game on the quiz if I asked you to calculate your K value, but if I gave you all the data. So do make sure you review the lab handout for flexible wall permeameter testing. Make sure you look at the interpretation of the lab data and how I did the interpretation of the lab data. So I've given you the answer key to how you would do the interpretation, and I've shown you on the Excel graphs. So make sure you take a look at that. That will help with the lab quiz. I think we can take a break. I have two options for you. The next unit is Darcy's Law and measuring hydraulic conductivity. I know you guys already covered Darcy's Law in second year, so I just made a brief PowerPoint presentation with a review of Darcy's Law, so you guys can take a look at that on in your own time. The next unit I can review with you is measuring hydraulic conductivity. I wouldn't say it's an overly difficult unit. It's a lot of just plug and chug into formulas. I'm happy to go through it with you guys, or if you guys would rather work on your ARP reports, that's fine as well. What works for you guys?
I actually had a question. If module 15 is on the test, does that mean we're going to be going through FlowNet?
Yes, that's next week.
Okay, so there's FlowNet stuff on the test.
Correct.
Okay.
That being said, I'm not going to ask you to draw a FlowNet on the test because I just don't think that's something you can draw with a time crunch when we can't have the tutorials in person. You'll have an assignment associated with FlowNets where you'll physically have to draw a FlowNet, but you'll have time to be able to work through that and then work together as groups. And I'm here to support you. The theory related to FlowNets will be on the test, but you physically won't have to draw a FlowNet on the test.
Is the assignment a group assignment or is it individual?
It's individual, but you can work on it in groups if you like. So everyone has to submit their own, but I'm available for assistance. And you know, if you learn better by working in groups, I'm not opposed to students working in groups on the assignment. Just they have to submit their own assignment in the end. What do you guys think would be best for you guys today? Do you want me to go over measuring hydraulic conductivity, or do you guys need time for ARP?
Yeah, if it's pretty straightforward, I could look at it in my own time.
Yeah, it's mostly just plug and chug. So there's formulas, and then you can plug and chug through the formulas.
Yeah,
But
I don't
I'm
see it.
happy to go through it. Whatever works with you guys. Is it only Sean and Kelly actually on the line? Oh, I can't see. Oh, we're down to 25. Okay. Okay, well, why don't we call it, because no one has said please go through it. I will be available to answer questions on that material next week, but next week we're going to concentrate on flow nets. But if there are questions on it, I'm happy to answer questions on it in the interim, or I can answer them next week. I'm also available today if you're not working on ARP and you have questions on GM2. Yes, Clive. Yeah.
So just to reiterate, you said that the quiz is due Thursday next week.
Correct. It's due on April the 8th, I believe at 5 o'clock. I'll double check the time, but it's due on April the 8th. Correct.
And what are we doing next Friday?
Flow nets.
Just going over FlowNet?
Yes.
Is that only going to be from 9 to 12?
Correct. Yes.
Okay.
And I don't even know if we'll go for 3 hours, because a lot of flow nets, I can go through the theory with you, but a lot of flow nets is just practice, right? So you get more from practicing than watching me do it. It's sort of like an art. So I'll give you little tricks of the trade on how to draw flow nets, but then you physically need to do it yourself. So I think
Is there
assignment...
another, oh, sorry.
No, go
Is
ahead.
there another modeling system that it's similar to that we've used already?
No. There's a suite, like within GeoStudio, there's something called SeatW that will draw flow nets. But I'm not aware, unless you did something in Mike Robb's class on flow nets, that, so flow nets tells you or allows you to calculate seepage under an embankment structure. So that's what flow nets are used for. And they're also used to determine the stability of a structure. So if your critical hydraulic gradient's been exceeded or not. So that's what flow nets are used for. Did you guys do anything like that in Mike's class?
No, not really.
Yeah. So I can't think of a modeling software that you guys would have used in the past. But that's what we're going to limit our class to next Friday, is just flow nets and talking about gradients. Your test. Do you guys want to take a look at your test? Or do you want me to set up a time for you guys to look at your test?
Yeah, if we could take a look at our test, that'd be great.
Okay. I will open them up. And then if students have individual questions about their test, they can approach me after. So I will open those up for you guys. So that will take me a few minutes. Otherwise, you guys are free to go for the day. And as always, I'm always available to help you guys. If you have any questions or if you just want to talk about example problems or whatever, I'm always here. So don't hesitate to contact me. Otherwise, have a great day and have fun working on ARP. I'm looking forward to reading all of your reports. So Clive, just stay on the line. I'm just going to go and open the test.
Hey, Elena,
Yes.
for the reports, when we submit them, are you going to be giving like what a potential grade would have been, or is it just going to be like comments or what?
It'll be comments on how to improve your report so you can get an A+.
Okay.
So all the comments I provide are so that you could get an A+.
Yeah. Okay. Awesome. Okay. Thanks.
Yeah, no problem.